Okay. Welcome, everyone. It's my pleasure to introduce Sergei, who's going to be talking about going to the other side. Feel free to start whenever you're ready.
Yes, thank you so much for the invitation. Let me make it full screen. I won't be able to see questions in chat, so please feel free to unmute yourself, ask questions. Let's keep it informal. In fact, I don't think I have too many slides for the entire hour, so I budgeted more like 45, 50 minutes of the talk, plus questions and discussion. There will be questions to the audience that I want to ask. In fact, I think I may be able to get out of this more than you from this talk. Apologies ahead of time. Right, so thank you for coming. And what I'll tell you is this interesting phenomenon that bothered me for past probably 5 or 6 years now. It's been a while, and it's a very curious phenomenon. So I didn't know what to do with this, how to properly place it in areas of mathematics. And I say areas because it seems like it does not belong to a single area. I'll illustrate this as I go along. And this phenomenon is something that this is going to the other side. It was coined in a paper with Miranda Chang and various other collaborators. And more recently, the reason I'm talking about it here is I think we managed to shed light and to some extent solve the problem in the recent paper, which appeared just a couple of weeks ago, maybe a week ago, with a video costing. Who is analyst in Ohio, Gerald Dunn, who is mathematical physicist Connecticut, and my math student, Angus Gruen here at Caltech. And this, if I were to summarize in one line what this talk is about, it's about this phenomenon I mentioned, which is mysterious, but it's basically an operation. It's a bijective operation. It maps one side to the other side. So think about two hands that each of us has right hand and left hand, and it's basically this operation bijection that sends left to right or right to left. This is actually not figurative speech. Later in the talk, you'll see in what precise sense this is actually left to right and right to left. So it is an operation, it is bijective, and one can call it duality because there are two sides involved. So that's what it is. Now, what is this operation? So here I compare it to mirror symmetry or reversing orientation. So this is something that is actually also quite accurate. This is a very good analogy to keep in mind. There is mirror symmetry already in algebraic geometry that studies equivalences of categories or other quantities associated to Calabi-Yau varieties, and that operation is also bijective. So the one we're going to talk about today is also very much of the same nature. In fact, it shares some of the underpinnings and origins with mirror symmetry, which is much more famous for Calabi-Yau varieties. And it also shares some features with this particular picture here, which is reversal of orientation once we reflect topological space in or some objects across some plane or hyperplane or switch orientation, we get this very similar thing to what we're going to see today. Now, I understand that this is more of algebra seminar, so hopefully many of you are more interested in algebra, and this will be definitely present today. And I'll be happy to answer questions and say more in the discussion, but I'll make this talk actually very balanced, and algebra will take only 30% of this talk. And the other, or 33%, the other 2/3 will be distributed among other areas. For instance, I'll mention actually physics a little bit. Hopefully, if you're familiar with the relation between, say, Virasoro algebra and conformal field theory, that shouldn't scare you too much. And also areas of mathematics, which again, hopefully are not too scary. For example, low dimensional topology will be yet another area where this phenomenon or operation or bijection or duality has a meaning. And more precise punchline of this talk, which again, I'll try to make sort of colloquium style or broad audience, is that this operation surprisingly makes sense in all these different areas, and it goes by different name or it's implemented in a completely different way, but results agree. And to me, this is surprise. So that's why I was quite puzzled in a very good way about this for 5 or 6 years now. That it seems there is something going on which is completely consistent across different disciplines in mathematics. So I find this quite fascinating, and I don't have a good explanation to it. So that's why I want to emphasize it from the start, so that if later, either a week later or maybe a year later after this talk, you have some ideas, I think it would be amazing to unleash the true meaning of this operation or dig deeper and see what it is. So I'll of course tell you what I understand, but I think the main message is that there is a lot more to be said about it. So this unreasonable effectiveness, in the words of Wigner, is quite surprising to me. Here, I didn't even put on the list various other areas of mathematics which will enter the stage. For instance, I mentioned in the previous slide that Ovidiu Costin, a collaborator of mine in this project, is his area is analysis, in fact. And we'll see that indeed this operation also makes sense in analysis, and there are many other areas such as number theory, for instance, which are not even on this list, but surprisingly this operation or bijection makes sense in all of these areas, and again in a surprisingly consistent way that I don't understand. So we'll deal with various quantities in this different areas of mathematics, many of which have enumerative origin. So for the algebraic audience, I can simply say, or in the context of vertex algebras, that will be, for example, we can be dealing with characters of vertex algebras, chiral algebras, and actually logarithmic vertex algebras will play a more important role here in this talk. But in this other areas of mathematics that I mentioned, we have to have a different formulation of what a function of Q with given properties is. So this typical, again, this will be the star of the show for the rest of the talk. We'll deal with Q series, which starts with some not necessarily integer power of Q, but then all the relative powers of Q are all integer and coefficients are all integer. So in the context of vertex algebras, of course, we know that these coefficients are either dimensions or perhaps graded dimensions or super dimensions of our modules of some infinite dimensional algebra that we want to study. In other contexts, you should think about such functions as counting something. So the integrality of these coefficients in other areas of mathematics that I mentioned, for example, in low dimensional topology or even in physics, will be that the integer coefficients here are counting various things with signs. So that's going to be a general common theme, or it's something I can say about all these different interpretations. So here is a real life example. For example, we'll take a function like this. It has some fractional power of Q multiplying the Q series, and in this case, it can be written in this closed form. Any questions so far, and can you hear me well?
We can hear you very well. Any questions so far? I don't think so.
All right, good. Feel free to interrupt at any point, ask questions. So let's start with this function, and our first exercise, which is something we can ask most undergraduates, and it's a lot of fun. So let's write it in this closed form as is in the second equality, starting with f of q, and do the following. So here we have a numerator and denominator, which are So numerator is some power of q with sign, and denominator is a finite Kuppelheimer symbol. So it's basically a rational function q. So what we can do is now take q to q inverse. That's going to be the operation that we're going to be discussing in every single term in the sum, and even here up front if you wish. So, but then we can multiply numerator and denominator in each term by sufficient power of q so that it becomes still expressed in terms of q rather than q inverse. So of course, what we're doing more mathematically is we're trying to find analytic continuation of this expression from, say, inside of the unit disk where this q expansion is defined. When we expand it in powers of q, we're assuming that q is inside the inside the unit disk, so that each subsequent term is smaller than the preceding one. And once we try to write it in terms of q inverse, we basically try to go outside. So that's basically what we're asking. So here, this operation is easy to do in one line on the back of the envelope, because yeah, you replace q to q inverse, this becomes q to the minus something. Same with Boheimer, you multiply it by power of q, and you clear denominator. I mean, you do simple algebra, you quickly get this, that each term in the resulting expression has this form. And now this is completely different q series. So that's the bijective operation that we're going to discuss. So the way I phrased it here, it's extremely concrete. It's completely non-obvious that it's well-defined, that it makes any sense, if it's unique. And these are kind of questions, exactly the kind of questions that we'll discuss in the rest of this hour. But operation itself is basically that simple. So anywhere in life, in any area of mathematics where you can see function of q roughly of this form, for example, character vertex algebra, or some enumerative partition function that counts some types of partitions, or any other combinatorial object, or maybe geometric object, or for example, elliptic genus also has the same properties of topological manifolds. So there are many areas of math where you can phrase this question about q going to q inverse and trying to rewrite the result back again in terms of q. So is this clear? Any questions? Okay, good. Right, so this example is actually quite nice. And again, this is the operation that the talk is going to be about. Of course, I'll try to phrase it in more algebraic way in terms of chiral algebras that will show up later. But again, you can think about characters for the start if you wish. And this is what we're going to discuss. This particular Q series is happens to be a Q hypergeometric function, Q hypergeometric series. That's how it's written. And I used this particular property, namely that it's written as Q hypergeometric series, to do this operation. And in this particular case, it is true that it converges both inside and outside of the unit disk with respect to Q. It does not converge on the unit disk, so that's something you can check. But there is this very nice continuation, and so far I got it in a very easy, extremely simple, cheap way by just replacing each term, multiplying by common power. But of course, this depends on whether I can write my function in such Q hypergeometric form if I want to do it seriously. And such Q hypergeometric form may not even be unique. So first of all, it may not exist. That's one thing. And if it does exist, it may not be unique. So then I could get different candidates for the answer, what it means to have this dual, which I denote with a check, going to the other side. So that's this operation of going to the other side at the level of functions. And then the rest of my talk, I'll try to decode what it means more fundamentally, and again, how it's unique, and so on and so forth. So at first, when I came across this, again, 5 or 6 years ago, people told me that, oh yeah, it's probably a curious phenomenon that should not exist. It should not have a meaning. It should not be unique. But I think the evidence that I collected over this 5-6 years with various collaborators whom I mentioned is basically to the contrary, that it's actually unique. And part of our work with this recent work that I mentioned is precisely to establish uniqueness. Of course, one needs to develop more serious mathematical machinery for that. And more interestingly, that it does play a role, and the result actually agrees across many disciplines. So that's what I'll try to explain next. Another comment that I want to make is that here with this particular functions or functions like that, one can actually also approach this operation of going to the other side or replacing q to 1 over q morally via Rademacher sums. So that's a method that we discussed in this paper from 5 or 6 years ago that I mentioned earlier. To me, and it's a very general method, so it works. There is basically a recipe how to implement this in a more systematic way, not just a back of the envelope calculation, which is of course very cute, but suffers from uniqueness. Except that this is very heavy machinery that is not easy to implement. It's not something that I can program on a computer and apply to many functions or Q, given as presented as a Q series, for instance, if I have characters of different logarithmic vertex algebras, which I'll discuss later, I cannot immediately apply this method of Rademacher sums to obtain lots of answers in one day. What will happen is that I can apply this method, it's general enough, but it will take probably, at least for me, a whole week to do it for one example, another week for another example, so it's not too efficient. I mean, maybe with some practice, one can do it in a day, but it's still quite heavy computation. So what we need is basically two things. We need conceptual role of this operation that I mentioned earlier. So that's something I'd like to understand. And we also need easy to use, very practical method. If somebody gives me such a Q expansion, I don't even have to know where it came from. It could be character of logarithmic vertex algebra. It could be of a numerative origin. I need a machinery such that with a punch of a button, I can produce the alternative. I mean, there's this dual version going to the other side. So that's going to be the goal, to uncover both of these questions. So then this is the question. So we should have some class of examples to use as a litmus test or a stress test. Whatever methods we're going to develop, we should have some class of maybe limited class of functions or Q series to play with. Of course, we should be able to apply it to complete generality, and the method will be completely general, but for testing it, I'll restrict in this talk myself to very simple but quite elegant class of functions, which are called false theta functions. So these are basically like theta functions. They define a sum over a lattice of q to some quadratic power of this lattice vector. So this is an example where it's one-dimensional. I mean, the lattice is one-dimensional, so it will be good enough for many purposes, but of course there is high-dimensional version of lattices, and they play a role. I mean, it will be generalization, and many methods that I'm just going to describe will work perfectly fine, but it won't be needed. Even with this class, we'll have a lot of fun. So just like theta function, it's a sum of a lattice q to something quadratic, but unlike the usual theta function, the signs may alternate depending on this congruence condition. So it could be plus minus 1 here, that's this psi. Again, don't be scared, this psi just plus minus 1 depending on congruence of n with respect to some period p, and therefore such object is specified by choice of p, that's integer, and by choice of a, which is runs from 0 up to 2p, basically. So these are called false theta functions. A big enough class, fun enough to play with. They don't have modular behavior like theta function. They have some spoiled modular behavior, which is good, or good in the sense it's interesting. And they will appear as characters, or rather combinations will appear as characters of logarithmic vertex algebras. In particular, the example I showed you on the previous slide, this one, where we did everything super explicitly just by hand on the back of the envelope, is a linear combination of such. So it has a p equals 42. This is very much like the Meaning of Life and Hitchhiker's Guide Through the Galaxy. And it's a linear combination with different values of the second integer a, where it's equal to 1, 13, and so on and so forth. So what's interesting is that in many domains of mathematics, where this operation of going to the other side appears, it's often we see functions which are, if they're expressible in terms of such false theta functions, we usually see combinations of false theta functions. And this could be characters of logarithmic vertex algebras or some Q-series invariants of 3 manifolds or knots or whatnot. And for those, I'll show you different methods of constructing this dual going to the other side. And then we'll discuss also, again, BOA origin of it and other things. But one question that also existed since early days of the subject, going back to at least 5-6 years ago, is, okay, I showed you the dual or the other side of this function on a previous slide. That was exactly the starting point f of q, and we did f of q check. But what if I ask for other side of just individual ingredient, just single false theta function? Surprisingly, one by one, these false thetas rarely appear in logarithmic vertex algebras or in quantum topology or in other domains. So they somehow appear in combinations. And one question was, is it important for this whole combination to be a combination to have this other side in the first place? And in other words, can one produce a dual, in the sense, on the other side of false theta function for any p and a, for all possible values of p and a? So originally the answer to this question was no. So when I specifically asked this question to many people who had some experience with false theta functions, number theorists, analysts, and they all told me that, yeah, the answer is expected to be no, that we should not expect this. However, in this recent paper that I mentioned on the first slide, we actually claim that the answer is yes, and provide a very constructive recipe, basically constructive way of producing this psi p a dual for any value of a and p. So this was quite surprising, at least to me, and I want to explain where it comes from and how. So this was breaking the expectation of early days. Like I say, this false thetas and even more general classes of such functions appear in many domains of mathematics. For example, they appear in quantum topology, where one can study quantum topology is usually a subject that works with quantum groups as input data and produces invariants of 3 manifolds and knots as output, usually packaged in some topological quantum field theory that tells us how to build this invariance by cutting and gluing. In this case, the relevant topological quantum field theory is actually decorated by choice of spin C structures on 3 manifolds. So that's very interesting for quantum topology purposes. For this talk, it's probably completely irrelevant. And these false theta functions that I introduced on the previous slide, they are invariants of 3 manifolds which appear in this particular decorated TQFT. I'll say more about it later, which is associated to quantum groups at generic values of Q. So Q here is parameter of the quantum group in that TQFT. So in that area, there is a way to produce the dual, and I'll tell you more about its origin from quantum topology perspective a little bit later, but for practical purposes, there is nice work by Sang-Hyuk Park on this particular TQFT associated to quantum groups at generic Q, where we're asking what happens if I replace Q by Q inverse, kind of roughly, and it allows us to produce duals for particular combinations of false thetas. For example, this is just one of possible combinations, but it illustrates the point that I showed you earlier, that usually it's some combination of these false thetas, not just only one of them appears, but several of them. And for this combination, one can construct a dual, so it's given by this explicit form. So it's not maybe terribly important what this is. Again, if you want to see more details, I recommend this paper. But there is I mean, since I'm reviewing different areas of mathematics, I have to say that there was already an operation that existed in this field of quantum topology, which allowed to produce some duals to go to the other side in some cases, but it wasn't generic enough to say that we can do it for a single false theta function, for example. But there were some combinations where we could do that. So this is good news and bad news. Bad news because it's only partial answer. It's incomplete if somebody is interested in just individual false theta. But it's a good news because for any alternative method of producing this dual or going to the other side, there will be a test or there will be a check because we can compare to this formula in quantum topology and many other domains where this operation has a meaning. And we can ask, does it agree? And what happens if we try to send Q to Q inverse? And again, re-express it as a function of Q. Basically, is there a such analytic continuation? So any questions so far? So let's practice a little bit. I'll soon get into more serious things involving logarithmic vertex algebras, but suppose our counting function is much simpler. So for example, it could be counting two-dimensional partitions, such as Dedekind eta function, or it could be simply geometric progression, which is counting the spectrum of harmonic oscillator. After all, Virasoro algebra is much more interesting algebra, and its modules produce more interesting characters and capture the spectrum of two-dimensional CFTs. This is just a basic quantum mechanics, after all. So what would happen here with such simpler functions if I were to take Q to Q inverse and then try to write it in terms of Q? Okay, so let's do it. This geometric series obviously captures is a trace over module. In this case, it's a very simple one where there is one-dimensional space at each grading for each value of the conformal vector, if you wish. And that's why this geometric progression is extremely simple. It starts with a Q to the half, which of course is very famous Maslov correction to the leading power of this energy or conformal vector for harmonic oscillator. And in any case, we can just take this expression, which is encoding the spectrum, and take Q to Q inverse. So that's, of course, what we get. But then we want to rewrite it in terms of Q. So we multiply both numerator denominator, just like we did before, by sufficient power. In this case, it's Q to the power 1. Denominator becomes basically Q minus 1. So we again reshuffle it to bring it to original form at the expense of getting a minus sign over here. So what's interesting, we see that this is almost self-dual, this bijection or going to the other side for harmonic oscillator basically almost turns it back to harmonic oscillator, but we get this minus sign. And this minus sign is interesting. It doesn't mean that suddenly this bosonic harmonic oscillator became fermionic. Actually, that was one possible speculation about, I don't know, 5 or 6 years ago when the subject started. For it to turn fermionic, this 1 minus Q would have to go to numerator. Of course, this didn't happen. 1 minus Q remained in the denominator, but we got a minus sign overall in front. And that's a sign of something derived that will reappear later in the talk. So it basically means that there is something higher, for example, higher cohomology in a certain sense. And again, in the context of VOAs, we'll be able to make it more precise. I mean, it will be more meaningful here. It's, of course, just an artifact. There is no minus sign if you do the same trick, if you do the same operation with Dedekind eta function. Here, this Q to the 1 over 24 helps, in fact, but the problem is more interesting. So again, we start with infinite product. That's the usual way of writing Dedekind eta function. We replace Q by Q inverse. And now we want to do the same thing. We want to multiply each term by sufficient power of q, and what we get is we get q to huge power up front, which is 1 plus 2 plus 3 plus 4 and so on and so forth. Of course, we know how to sum the series 1 plus 2 plus 3 plus 4. It's going to be usual zeta value, which is minus 1/12. And as a result, the eta function actually is completely invariant under this bijective operation of going to the other side. So this is fun exercise that nothing happens to it. That's actually quite nice. So any questions here? We're slowly getting more and more practice with this operation. Okay, so I already mentioned quantum groups briefly, and in quantum topology, certain invariants associated to it. I'll tell you a little bit more about them. And of course, via Kazhdan-Lusztig correspondence, there is a relation between various gadgets that we attach to affine Lie algebra, vertex algebras, and quantum groups. And here, for example, this Kazhdan-Lusztig correspondence is studied by Kashewara and others. Usually we pick a choice of sign of the level where we do it. So in particular, one of these interesting aspects of the talk, even though I said in the beginning that this operation that we're going to study today is very much like reflection symmetry between left hand and right hand, our left hand and right hand are pretty much similar up to reflection. But what's interesting is that in many of these domains of mathematics that I'm going to mention, this operation, even though it has the same origin, it is kind of bijective symmetry that's reflecting something, is going to be quite asymmetric. And we already can see this in the realm of vertex algebras or quantum groups, where negative level and positive level are quite different in general. So in particular, this series of papers and many other papers that studied Kazhdan-Lusztig correspondence in late 80s and early 90s, they usually focus on negative level, or in some sign convention, it would be negative level, whereas positive level is hard. And this will be especially interesting, or it's more, I shouldn't say hard, it's more interesting, and it will be extremely more interesting, even so, more so for us, because I'll be interested in logarithmic vertex algebras. These are the ones for which false theta functions that I mentioned earlier appear as characters. And I told you that for quantum group, a generic value of Q, there is some topological invariant in quantum topology. So this is usually called, z-hat invariant, which in its construction is basically based on Reshetikhin-Turaev type construction. It follows the same rules, except that instead of finite dimensional modules, we use infinite dimensional Verma modules of both lowest weight and highest weight in this construction. I don't know what's the Kazhdan-Lusztig dual of this is. In other words, what's the right vertex algebra or lattice model? If somebody has good ideas, I'll be delighted to discuss it and hear your comments and thoughts. We should definitely talk. But if we take this Q from generic value to root of unity, then some things are known. We typically get from this generic quantum group at a generic Q some form of small quantum group. It could be unrolled or restricted quantum group, and there are many different close cousins and variants which are extremely interesting. In following this Kazhdan-Lusztig philosophy, one can ask, can I match either the center of it or maybe whole representation category with analogous objects on the vertex algebra or chiral algebra side? And here many more things are well known and better understood. And these are the ones for which characters are exactly these false theta functions that I mentioned earlier. So therefore, one can try to focus on this side of the diagram. And again, this will appear in its own right as well. And here, basically, if we work with a negative level, we get some familiar logarithmic vertex algebras, such as which, for example, carry the name of singlet or triplet algebras. And then there are various generalizations. So these are precisely the ones for which false theta functions that I mentioned earlier appear as characters. And then there are many various cousins of them appear as well. But then we can ask what happens in the positive Kazhdan-Lusztig zone. So there, naively, what happens is that, I mean, nothing good happens because we basically turn the notion of energy upside down. So the password for this Zoom meeting is Virasoro, and then if you take Virasoro algebra and it's some module and turn it upside down, the energy is now going to be unbounded from below, which is not good at all. So something pretty bad happens, and there is this question actually has not been really addressed or understood until recently, and more recently, luckily, there is some work on it, which started with Arkhipov, Gates-Guri, many other people, and only in past couple of years, some of their students, and I believe one of them is student of Kamnitzer, the other is a student of Gates-Guri, made some proposals for what should be the Kazhdan-Lusztig correspondence for this logarithmic algebras at the positive level. The tools are quite sophisticated. They involve semi-infinite cohomology and fine Grossmanians and many other cool things. So this is super exciting, but it's not at the level where one can take this technology and compute the character. So in other words, we don't have good access to the modules of these VOAs in positive and negative zone for logarithmic VOAs. And this is the question that basically is VOA underpinning of this phenomenon of going to the other side. So again, if anybody has good ideas, let's talk. But this is the kind of question that we're interested in. Okay, so I promise that there are other areas, and I already mentioned briefly quantum topology and three-manifold topology. In four-manifold topology, there is another counting invariant which has to do with gauge theories. That's another area of math based on analysis and PDEs on four manifolds, where one can try to formulate various invariants, define various invariants by counting sheaves, for example, on four manifolds. And what one expects for purpose of understanding smooth structures on four manifolds is that the resulting invariant should be very asymmetric with respect to reversal of orientation. So if I replace four manifold by its mirror image, think about the first slides in this talk, by reversal of orientation, then if invariant is very asymmetric, this is actually good. So again, think about analogy with a positive negative Kazhdan-Lusztig zone where things are quite asymmetric. So for topology, this is a good thing. It means that such invariant has good potential to detect smooth structures. And again, there are many such invariants which look like Q-series, very much what we discussed. For example, Waffe-Witten invariants have the same form. They have the form of a Q expansion with exactly the same structure. They count some sheaves or what physicists would call instantons. And one can ask the same question, what happens if Q goes to Q inverse? That actually is exactly the same question as asking for orientation reversal on a manifold, because powers of Q are precisely the second Chern class of the sheaf that we're counting. And if we reverse orientation of the four manifold, then evaluation of the second Chern class will change its sign. So the question of sending Q to Q inverse is exactly the same question as switching four manifold and its orientation reversal. So then these operations also have some incarnation in physics. I'll be brief about physics, but this is yet another area where such phenomena appear of going to the other side. And in fact, they incorporate both quantum topology of three manifolds that I mentioned, this Q-series invariance, and the questions related to four manifolds, such as the one on the previous slide. One can start with a mysterious 6-dimensional conformal field theory and consider some form of fiber integration or push forward along either 3-manifold and 4-manifold, and then what one expects to get is basically dimensional reduction of this functor, which is 6D CFT, and one can get either 3-dimensional conformal theory or 2-dimensional conformal theory. So 2-dimensional conformal field theory should hopefully not scare you too much, because this is basically the subject of vertex algebras. But 3-dimensional conformal field theory may be a little bit more sophisticated, but yeah, mathematically more interesting, but less trivial. In the context here, where we associate 2-dimensional conformal field theory or vertex algebra to a 4-manifold, we can ask the same question: what happens if I reverse orientation of the 4-manifold? Then the resulting VOA is completely asymmetric. So what one can see is that left and right, which should be very symmetric, actually appear quite asymmetric. But again, this is good for the purpose of topologists. This is a good thing. This is great, except that we need to understand what this operation means. And here, for example, I list central charges for connect some operations with CP2 and CP2 bar, which differ by orientation reversal. And you can see that they're quite different. One is -5, so it's definitely non-unitary VOA, and this one is +31, so it's definitely, well, or it could be unitary, but they're quite different. So these questions in physics, so continuing now a little bit with physics, leaving topology for a second, appear in so-called 2D, 3D couple systems. So they naturally appear in questions if it have a 4-manifold and try to do this fiber integration or push forward. And if we cut 4-manifold along a 3-manifold, that's a typical operation topologists would like to do. Then what happens is that in this setup of this push forward or partial dimensional reduction, one gets a system where 2-dimensional field theory associated, conformal theory associated to half of the 4-manifold lives on the boundary of some 3-dimensional theory, which is associated to a 3-manifold here. So this goes by the name of 3D correspondence in physics. And in such context, where you have 2-dimensional theory coupled to a 3-dimensional theory, many of the phenomena that I described before are ubiquitous. So first of all, this plays a role in study of 4-manifold invariance from this cutting and gluing operations. Secondly, the same setup is actually relevant for defining physics of this quantum group invariance at generic Q that I mentioned earlier. And more recently, this in various works, we related this setup to logarithmic vertex algebras, which is also something I mentioned before. So this has been very active area of research in the past 10 years. We introduced these systems, 2D, 3D couple systems, with physics colleagues Abhijit Gada and Pavel Putrov exactly 10 years ago, and they gave birth to many different applications and 4-manifold, 3-manifold invariance, as well as this 3-dimensional realization of logarithmic vertex algebras. So in this setup, what happens is the following. So the vertex algebra in question roughly lives on a boundary of this 2D, 3D couple system. But this setup actually partly explains why this operation is very asymmetric, because see, in topology, in this 3D correspondence, for example, orientation reversal on a manifold looks like something very symmetric. We just replace 3-manifold by minus of the 3-manifold. And of course, there are these nice bijective pairs. So from topology perspective, there is not much difference between M3 and minus M3. The same is true about this 3-dimensional bulk of this physical setup. But this boundary condition is very asymmetric. It's a 2-dimensional conformal field theory. So we again get back to the world of VOAs or chiral algebras. But it's asymmetric because it's super algebra in right sector, which is anti-holomorphic, and it's usual non-super algebra in the left holomorphic sector. So conformal field theory in physics is combining two vertex algebras or two chiral algebras, holomorphic and anti-holomorphic. And in this particular context, they are very asymmetric from the start, because one is super algebra, the other is not, or one is super symmetric, the other is not. So therefore, we cannot expect that when we switch left and right, that's what parity or orientation reversal does, we just exchange the two sides, left and right. One has to undergo operation which makes it much, much simpler, and the other, going backward, will have to undergo some operation which makes it much, much more complicated. So this is reflecting asymmetry that I showed earlier in the talk, which appears in between positive and negative Kazhdan-Lusztig zones, and also in interesting invariance of 3 manifolds and 4 manifolds when we want to differentiate between left and right. So a while ago, in a study of example, which again is very physical, it has to do something with even QCD-like theory in 2 dimensions. This left and right sectors, which, as I try to emphasize, are very different, and the story involve 2 VOAs, one of which is usual, non-supersymmetric, that's basically WZW model. And the other supersymmetric side is Kazama-Suzuki coset model. So they share exactly the same modular properties, and in a way which can be paired together, but pairing involves level rank duality. So basically in this context, which is not the main question I was asking earlier, there is this operation of switching left and right. It does have a meaning, or going to the other side, but it's highly non-trivial operation, which at the level of VOAs takes Kazama-Suzuki coset model and turns it into WZW and vice versa. So my question then is, what happens at this, at the similar level for logarithmic VOAs? In particular, what would be the right counterpart of this false thetas that we introduced before, and which can be viewed as characters of this algebra. But hopefully by now I convince you that, well, one can formulate the question at a level of functions or characters that we can explain to undergraduates. The deeper meaning of this operation, of course, is at the level of full algebra and all of its modules. Okay, so any questions so far? So
I guess I have a comment, maybe question in your previous slide, Sergei. So your first arrow here between WZW and Kazama-Suzuki, you're thinking of positive integer levels. Well, at least the way I think of them.
right.
But you're thinking of rational theories, right?
Correct. Yes, correct.
I see. There's also a Kazama-Suzuki correspondence even when you are dealing with fractional levels.
Right.
So it is still true that you get the n equals to a fractional central charge as a Kazama-Suzuki dual for the SL2 one.
Yeah, so then question is based on its modular data. So let's have here some fractional levels. So question would be, does its modular data perfectly match some other VOA, something like WZW, for example, and that would be then, again, the relation between their characters would be exactly this operation of going to the other side. And of course, what I'm asking here is this huge generalization of this, to logarithmic world. Yeah.
Thanks.
But even in that case, it would be extremely interesting. So indeed, we can gradually start with something like this, take fractional levels, ask does the modular data match something purely bosonic? And once we find that, ask, okay, what happens to the characters? And basically, that's the question I'm exploring in this talk.
Gotcha. Thank you.
Right. So last part in the remaining 5-10 minutes, I'll basically tell you the answer that we proposed. And it involves yet another area of mathematics. So on the one hand, I apologize, I go across so many areas of math, But on the other hand, I think that's, to me, most exciting thing. I like building bridges, not barriers, between different areas of mathematics. And it's these bridges in this case that I find super exciting. So this is going to be bridge to analysis. So we propose in this last paper that I mentioned solution of this question via analysis, and the way it goes is as follows. So our original question was about function of Q. Let's think about some character, and we want to find its dual, which leaves far outside the natural boundary of this function f of Q. So to answer this question, it's actually useful to try to transfer this information to a different domain, in a sense that our function was supported strictly inside the unit disk, but we can ask what happens to it if I try to expand it to this domain, showing in pink a small neighborhood of a point q equals 1 in the Q plane. In other words, I can write Q is exponential of small parameter, either epsilon or h bar, and try to ask for this expansion. So then you can already anticipate that this is kind of a middle ground between f of Q and f of Q dual. And if we have this operation under control, then we can probably answer this question. And this is indeed the goal of this resurgent analysis, which does exactly that. It basically allows you to transfer the domain where your function is defined originally to some other area or region in the complex plane. In other words, it's basically analytic continuation in practice. The way it goes is first you go from Q expansion to this expansion, formal expansion in terms of epsilon or h bar. So this typically is a very divergent, pretty bad series for all practical purposes. Otherwise, this would not be a natural boundary of our f of Q. But then you divide coefficients in this expansion of the new with respect to new variable h bar by n factorial. So these coefficients grow very fast. That's why it's usually divergent series. You divide it by n factorial to make it convergent. And now, with respect to this new series, this is something completely new. This is actually a better defined function, and it's much easier usually in practice to understand analytic structure and analytic continuation of this object, of this function. In fact, the goal of this resurgent analysis, which is part of complex analysis, is to analytically continue to all of complex plane, but now in this yet another variable s. So you see, we changed variables a couple of times. We went from Q to h bar, which is expansion near Q equals 1, and now to this new variable s, which is the last one. And this is the most important one. This is a variable on so-called Borel plane, Borel after Emil Borel, who introduced many relevant tools here. And the question one is typically asking is, what is this function? What is an analytic structure? What are the cuts, the poles? And in resurgent analysis, if you know what this Borel plane or this picture looks like, you know everything. Why? Because then there is a tool or set of tools which allows you to do analytic continuation in pretty much any region you want. So first of all, you can define then this integral, basically take this function which you analytically continue to all of the Borel plane, you define the integral, and then you study this integral which has a lot of cool properties. The first of which is that it does recover the original series as a small expansion in h bar, but then it typically can be extended to all of the Q plane in the original variable. So I told you in the beginning that if you have the general tools, if you have technology, we should have some class of examples on which we're able to demonstrate whether the tools work or they don't. And one set of questions was associated to these false theta functions. Like I said, we didn't know what the duals were. We had no idea 5 years ago if the duals should even exist for individual values of a and p. And is this operation of going to the other side very special to combinations of these functions or not? So now we can answer all of this using this analysis, complex analysis, because Borel plane for any value of a and p is very simple. That's basically what it is. So the second step here, which is most important one, produces this function, which is very, very simple. It's a ratio of 2 sinches. So now you just have to analyze Borel plane associated with this function in terms of xi. I apologize. This is the same variable as s here. So for some reason, I changed variables. And yes, it has all kinds of poles, or rather singularities, because there is square roots here and so on, branch cuts. So we can analyze this and produce for any value of a and p a method which is very constructive. It is numerical because you have to do some integrals here and so on. There is no, maybe in this class of functions, there is a closed formula. We didn't actually look for it, but we devised a method which works for any function, starts with, for example, false theta function and produces the dual. So the method is numerical, and basically it's based on this resurgent analysis. So here you have what you see on this plot is implementation of this method for example, order 5 false theta function, which has this form. It has this plus, minus 1, or 0 coefficients that you saw in the definition in the earlier slides. They're all plus, minus 1 or 0. There are no absolute value 2, 3, and higher. But the dual does have 2s and higher order, higher absolute value coefficients. And the way it comes up is the following. So these curves on the slide basically show this implementation of this resurgent analysis, where what you have to look for is how these different curves, the red one, the blue one, the green one, they try to, you see, they try to approach some integer, and then they quickly go down where approximation breaks completely. So what you have to do is either, this of course can be done with any arbitrary accuracy. We can, improve it further and further. So it's not an issue. But for example, it's clear that this green curve is approaching 1 and then precipitously drops down. The blue does the same. It's also 1. And this yellow, for example, is approaching -1 and drops down. And if you know a priori that coefficients should be integers, then you can just read it off. So I forget what is the assignment of this different colors to different powers of Q expansion, but that's how you get coefficients 1, -1, 1, 0, 1, -2. And that's precisely what we encode in the answer. So this is sort of the procedure that we develop to answer this question in complete generality. Again, you give me such a Q series, could be a character, could be something. I don't need to know where it comes from, and we can produce in a very systematic and actually quick and easy to use way, the dual. In this particular case, the answer was known to Gordon and McIntosh. So they have a very nice paper on mock modularity from about 10, 15 years ago. And this example appears in that paper. But now, of course, we can do lots of new examples which never appeared anywhere in complex analysis or number theory, or again, I haven't seen characters of log VOAs analyzed or modules matched for positive, negative zone in such detail. And in particular, we can answer this question in the affirmative. I mentioned that it wasn't clear whether for a single false theta function, not just combination, but for a single false theta function, there are duals. One can take them to the other side, what the result should be. And this is one such example. For the order 7 false theta function, there is nothing I can compare it to. So it has never appeared in the literature. And this is the first prediction. As you can see, it's quite asymmetric because here we had coefficients plus, -1 and zeros. Here we have all kinds of coefficients. The absolute value will grow if we continue the Q expansion. So again, I don't know how to reproduce it directly from either VOA or any other method, but this resurgent analysis seems to be extremely powerful method which can take any function like this to the other side. And again, my punchline in this talk is that I try to phrase it in the level of characters of these functions of Q, but of course, the main punchline is that it does seem to make sense even at the level of algebra. So again, my best candidate is probably going from positive to negative Kazhdan-Lustig zone, or something similar to this pairing between, or the fact that modular categories can be matched between WZW and Kazama-Suzuki cosets. This operation has actually a very clear meaning in topology, just orientation reversal. So it is really reflection, and similarly in physics. So I guess I'll stop here, and thank you for your attention.
Thank you so much, Sergei. Let me stop the recording so everyone feels comfortable asking questions. Thank you.